So, welcome back after the short break, and we are talking about frequency response of the amplifier, and we have seen that generalized form of a network consists of CR circuit and RC circuit, and in between we do have an amplifier. Now, let me try to map that model, or rather actual circuit mapping to that unified model. So, say to start with, we do have a common source amplifier, and the circuit is given here. The circuit is given here for your reference, and if you see here, we do have the main part, main amplifier here, and then we are feeding the signal through this capacitor called say C1. At the output, we are observing the signal after removing the DC part through the C2. In addition to that, it may have some capacitive load coming from the next subsequent circuit. So, let you call this is CL. Now, if we draw the small signal equivalent circuit after obtaining the equation point and other things defined by R1, R2, then VDD and then RD, what we obtained in our previous discussion, we said that at the middle we got the main amplifier circuit, and here of course, it is the small signal equivalent circuit, where VDD it is VDD node, it is AC ground, and the transistor it is getting replaced by its small signal model, which is voltage dependent current source called small IDS, and its expression it is given by transconductance GM multiplied by the VGS. VGS is the voltage appearing across gate to source of the transistor. So, this is the VGS. So, based on this VGS, we are getting this current, and then that current it is flowing through this RD, and then of course, we are getting a voltage here. Note that still this is not an equivalent, but it can be easily converted into Thevenin equivalent. Namely, we can make the amplifier which is having a gain of minus GM into RD. So, the voltage here you can say equivalently whatever you say V2. So, this voltage here it is minus GM into RD into VGS, and of course, the corresponding Thevenin equivalent resistance it will be same as this RD. So, this part the output port part, it can be translated into this circuit, and once you translate this circuit in this form, then we are moving towards our unified model of the amplifier. Likewise, input side again these two resistors you can translate into equivalent resistance here, which it will be R1 parallel R2. So, what we can see here that C1, this C1, so this is the C1, and then this R in, which is R1 parallel R2, they are forming one CR circuit. This CR circuit is getting formed here, and then output resistance which is RD, and then this CL along with this C2 coming in series, they are these two are forming another circuit, which is of course, this is RC circuit, and this capacitor value it is basically C2 in parallel with CL, and its expression it is sorry, this is in series, this is in series. So, its expression it is C2 into CL divided by C2 plus CL. Typically, this CL it is much smaller than C2, rather C2 is much higher than CL, and this part it dominates. As a result, this becomes approximately CL. So, we can say that at the output we do have approximately CL. So, what we are getting here it is that the amplifier it can be translated into that unified model, which we have discussed just now before the short break, where it is having C1, then R in, and then across this R in the voltage it is VGS, and that VGS it is generating a voltage which is whatever minus Gm into Rd times this VGS, and then it is also having the Thevenin equivalent resistance Rd, and then we do have the output capacitance approximately same as the CL, and at the input we are giving the stimulus. So, now as I said that we do have CR circuit, we do have this is the amplifier part, and then we do have the RC circuit. And from that directly we can say that who are the contributors of the cutoff frequency and the gain. So, in the next slide I am just summarizing the same information. Yes. So, what we have for our reference, again I am just keeping this diagram we just now we have discussed, and this circuit we are mapping into this generalized form. We do have the C1 here. So, this C1 it is coming here, and the middle portion particularly this portion, the amplifier portion we are modeling in this form. So, I should say that this amplifier it is getting modeled into this one, which is voltage amplifier, where it is having three important parameter, namely R in. So, R in equals to if I say R1 and R2 coming in parallel, and then VGS is basically here we are calling it is V1, and then V1 multiplied by AV or A naught, that gives us the voltage at this point. So, we can say that this A naught equals to minus Gm into Rd, and then this Ro which is equals to this Rd, and then the Cl it is dominating compared to the C2. So, this capacitor it is approximately the Cl. Now, as we have said that the frequency response, now if you are asked to draw the frequency response or the Bode plot, particularly the gain plot, I think you will be able to do it yourself. Omega in log scale, right, and then the mid frequency range, the gain it is defined by this A naught. So, if I consider magnitude, so we do have the gain here, and then the lower cutoff frequency it is coming from C1 and this R in. So, this frequency it is 1 by C1 into R1 parallel R2. So, that is the lower cutoff frequency, and then upper cutoff frequency it is defined by this Rd. So, if I say this is the upper cutoff frequency, which is this Rd and Cl are defining. So, this is and then gain here it is of course in dB 20 log base 10 into Gm into Rd. So, I should say that this as we have discussed before, this CR circuit, it is contributing this part. So, this is CR part, and then the RC part, it is contributing this part. So, this is the RC part, and the middle portion which is coming from this part. So, this middle portion it is coming from this the amplifier. So, that is how we do get frequency response of the amplifier. Now, if you are asked to plot the phase also, so this is gain or magnitude. Sometimes it is also referred as amplitude. Now, if you are asked to draw the phase plot, what you can see in the mid frequency range, note that we do have a minus sign here. So, as a result, in the mid frequency range, the phase it will be. So, we will start from the middle, and then as you are. So, this phase is either you may say that minus 180 degree or 180 degree, and then it is having a roll off towards this corner frequency, and then it goes a step of 90 degree, minus 90 degree. So, this phase it will be, if I consider this is plus 180 degree, so this phase it will be 90 degree, and at this corner frequency it will be 180 degree minus 45 degree. So, that is 135 degree. On the other hand, here it is the step, it is the other way. So, the phase it rises here, and here also it will be having a step of 90 degree phase up. So, this is 90 degree plus. So, we may say that this is 270 degree at this level, and at this point here it will be this plus 45 degree. So, that is at this point it is 225 degree. Okay. So, in case if you are instead of calling this is plus 180 degree, if you are calling this is minus 180 degree. So, you need to change this one to minus 270 degree, and then this one you need to change to minus 90 degree, but whatever it is. So, we are getting this corresponding gain plot and phase plot easily by using this the unified model of the amplifier. So, similar thing it can be done for the CE amplifier. So, let us see what are the things we have done for CE amplifier. As I said, that is very similar. So, you may recall the CE amplifier with fixed bias, and this middle portion is the main amplifier, and it is also having this two signal coupling capacitor C1 and then C2, right. And in the middle portion, of course, we do have the transistor, and the middle portion can be converted into small signal model, which consists of this RB. We do have RB there, and then we do have RC here, and base to emitter junction we do have R pi. This is the part of the small signal model of the BJT, and then we do have the IC, small signal IC equals to GM into VBE. sorry, this will be VBE. So, this VBE, it is of course, the voltage between this base to emitter terminal or emitter node, or voltage across this R pi. So, here again this part it will be straightforward to convert into R in, or equivalent input resistance. So, R in equals to R b in parallel with R pi, and typically this is getting dominated by this R pi. On the other hand, the Norton equivalent circuit. So, this is of course, AC ground. So, this Norton equivalent circuit we can convert into Thevenin equivalent for our convenience, and once we convert this voltage dependent current source into voltage dependent voltage source, what we are getting is this voltage here, it is Gm minus Gm times R c into this voltage VBE. And then Thevenin equivalent resistance, of course, this will be same as this R c. And similar to our previous discussion, as I said that there will be load capacitance coming from the subsequent stage CL. So, the C2 and CL together, they will be giving us giving the load to this circuit, and typically this C2 it is much higher than CL. So, the series connection of this C2 and CL together, it is approximately with this condition approximately CL. So, at this output node we do have the CL. So, similar to the common source amplifier, again here we are getting RC circuit or rather CR circuit constructed by or consist of the C1 and R in. In the middle we do have the voltage amplifier defined, its gain it is defined by Gm into Rc with a minus sign, and then the next one is the Rc circuit. So, here again we can map this amplifier into the unified model to get the frequency response of the overall circuit. So, that is what we are summarizing in the next slide. Yes. For your reference, again I am keeping this circuit, and this circuit it is getting mapped into this unified model, and the R in, it is in this case R b in parallel with R pi, which is approximately R pi, and R o equals to R c, and then A naught is equal to minus Gm into R c. Okay. And here again the procedure it will be same. If you are asked to draw the Bode plot of the entire circuit, what we will be getting here, it is in the mid frequency range you will get a decent gain defined by this A naught, and then the lower cutoff frequency it will be coming from the CR circuit. So, the lower cutoff frequency say omega 1, it is 1 by R in into C1, and the on the other hand the upper cutoff frequency it is R c, and CL they are defining. So, 1 by R c into CL it is defining the upper cutoff frequency, and this is the gain which is 20 log base 10 Gm into R c. I think that is the frequency response of the normally used simple voltage amplifier. Now, I must say that few more information that if you recall the so far we are talking about the fixed bias circuit So, in this circuit we are not having any emitter register, and in case if we put emitter register here, say R e, and of course, then I have to put voltage bias here, maybe this is R 1 and this is R 2, and so that gives low gain. The corresponding gain, it is simply R c by R e, and to get back the higher gain, we need to bypass this R e by say C e. Now, this C e, it is also having some role to play to define the upper or lower cutoff frequency, that can be seen later. So, probably we need to have a dedicated class to discuss about the frequency response of this self biased common emitter amplifier. So, yeah, so the so where all let me instead of stretching today's class towards the CE amplifier with the self bias, let we summarize what are the things we have covered today. Okay, before I forget, actually this should be self bias. Okay. Anyway, what we have covered today, it is the RC circuit frequency response we have revisited, because this frequency response of RC and CR circuit, it helps us to get the frequency response of an amplifier. And what we have seen there with these two examples independently, that the transfer function and the frequency response, particularly transfer function in Laplace domain, in S domain, and the frequency response while you are changing the frequency in omega along the omega line, we have seen that they are definitely they are related. Particularly which is important thing is that the pole in transfer function in Laplace domain and the cutoff frequency in the frequency the response, they are directly related. So, what we have seen is that we started with simple CR circuit, and then we have seen that for CR circuit the location of the pole defines the lower cutoff frequency of high pass nature, and pole location of RC circuit on the other hand, it defines the cutoff upper cutoff frequency of the low pass filter. And those frequency response, if we combine together along with the middle ideal amplifier, then they are helping us to get the frequency response of common source and common emitter amplifier. So, in today's discussion, that is what the main thing is, that how we make use of CR and RC circuit along with the ideal amplifier to get the frequency response without really going in detail of the analysis or equation. Intuitively we can say that which are the contributors of the which cutoff frequency and so and so. Now, in this module, as I said that we need to cover some more things. So, we do have the pending items listed here, the frequency response of CE amplifier having self biased. So, it requires some dedicated class to cover this frequency response, and whatever the analysis we have done, we can make use of that to find the numerical value of the cutoff frequency of a filter and so and so. So, we need to cover the numerical examples, and then we will be talking about the design guidelines. Note that under this design guidelines, we have talked about design guidelines of CE amplifier for both self biased as well as fixed bias, but primarily that is related to the mid frequency gain. Cutoff frequency we have somehow we have touched, but we did not go in detail. Now, we like to cover similar kind of things for common source amplifier. This thing we need to cover, and also the information about the frequency response and the analysis of frequency response of CE and CS amplifier, how they will be helping us to find selecting the coupling capacitors, namely C1 and C2 and CE. They are also in fact part of the design. So, once we cover the frequency response, then we can revisit the design guidelines of CE amplifier to get rather more appropriate expression of C1, C2 and CE. I think that is all I need to cover in this module. So, we will be coming back in the next class with this pending items. Thank you for listening.